A Copeland digital scroll compressor. Air conditioning and heat pump technology that allows capacity control better than any other variable capacity compressor can. From 100% down to 10%. 30% of operating costs can be saved because air conditioning systems spend most of their time at less than full load, and digital scroll compressors use less power at reduced capacity. Here you can see inside the digital scroll compressor and glimpse its unique method of operation. It's very simple really. When it pumps, and when it doesn't, it doesn't. Come on a journey as we tell all about the magic of digital scroll compressors, how they work, what the service engineer can expect to experience, and how they will benefit the end user. In just a few minutes you will be armed with the knowledge necessary to understand the technology and be able to spread the word to other engineers and, more importantly, the customer. First, let's see a real-life Copeland digital scroll compressor in operation. This was filmed in Temperzone's own R&D test laboratory, so there is a little bit of background noise. The main noise to concentrate your ears on is the clicking of the solenoid valve, which switches the pumping action on and off, and the tone of the compressor, which changes from when it is under load and when it is effectively bypassing. In this second shot you will just be able to make out the solenoid valve in the top right hand corner of the screen. Here it can be seen more clearly. The tone of the compressor is clearly changing immediately after each solenoid switching operation. The compound and head pressure gauges here clearly show how the suction and head pressures are effective as the compressor pumps for a few seconds and then bypasses for a few seconds. A serviceman once complained to me that there was something wrong with the system, as the pressures were all over the place. He couldn't get the system to settle. I asked if he could hear the solenoid valve clicking every few seconds and about the compressor tone changing, and then explained how these are normal operational symptoms for a digital scroll compressor at part load. How long it stays pumping compared to how long it is bypassing is based on how much load is required at that time. Let's have another quick look inside to see what is happening. The scrolls, when together, are initially pumping, but then as the solenoid valve lifts the top scroll, the pumping ceases. The effect can be seen here on this compound gauge. As the solenoid valve releases, so the compressor pumps and the pressure falls. When the solenoid valve energizes, the pressure rises. Conversely, on the head pressure gauge, as seen here, the pressure rises when under load and falls as the solenoid valve energizes. The same is reflected in the amps that the compressor is drawing. On this compressor, when under load, the amps drawn are about 5.6 amps per phase, dropping to about 3.8 amps per phase when the solenoid valve is energized. This is where the power saving occurs. On this example, the compressor is only using 68% of the energy when unloaded. The average power usage is dependent on how much time is spent on either cycle. Usually, the driving signal is a variable voltage signal such as 0 to 10 volt DC that is then converted to a pulse width modulation effect that is sent to the solenoid valve. Okay, time to look into the workings of the digital scroll compressor. First, let's familiarize ourselves with the standard scroll compressor. The motor, shown in blue, drives the shaft, shown in yellow, and this has an eccentric at the top end to move the bottom scroll, dark red, in an orbiting motion. The brighter red is the fixed scroll at the top. Here we see the two scrolls, the top fixed scroll to the left and the orbiting scroll with its guide slots to the right. When the scrolls are inserted in each other, if you could see inside, it would look like this, the black spiral being the top fixed scroll and the grey being the bottom orbiting scroll. Here we see 5 phases of operation. In the first picture, we see refrigerant gas being drawn in between the scrolls. The second picture shows the gas being trapped by the bottom scroll closing in on the fixed scroll as it orbits. The next picture shows the trapped gas is compressed as the pocket the gas is in becomes smaller in volume. This continues until, as in the fourth picture, the discharge pressure is reached and the compressed gas leaves via the discharge port in the center. The last picture shows that the process is continuous As one pocket of gas is being compressed, another right behind it is being drawn in, and a third in front of it is being discharged. As the scroll has two entrances, this is actually duplicated. There are some specific features of Copeland scroll compressors that other compressors don't have. Radial compliance allows the scrolls to separate sideways should any debris or liquid droplets enter the scroll. Axial compliance is by a patented floating seal that maintains even and constant pressure on the tips of the scroll. The tips are metal to metal contact, so tips don't wear out, unlike other designs where different materials are used and are fixed to the scroll tips. Scrolls wear in and don't necessarily achieve full performance on initial startup. Now let's move on to the digital scroll concept. As you can see from the history, it is a fairly new technology and really only introduced to air conditioning and heat pump applications around the turn of the century. Temperzone introduced digital scrolls into commercially sold units around 2006 and 2007. Digital scroll technology does not require any complicated electronics or the multiple electronic expansion valves usually associated with inverter compressors. The concept is simple. It modulates. It can modulate down to 10% and anywhere between 10% and 100%. It really is quite simple. The previously fixed scroll of a standard scroll compressor becomes a non-fixed scroll, and this can be lifted to separate the scrolls axially by just 1 mm. The compressor then no longer compresses the gas and the system starts to equalize. A few seconds later the scrolls are back together and the compression cycle continues. Let's assume the driving signal is a variable voltage signal such as 0 to 10 volt DC. This is then converted to a pulse width modulation signal that is sent to the solenoid valve. If the required load is about 25%, then the compressor will run loaded for 2.5 seconds out of 10 and be unloaded for 7.5 seconds. At 90% it would run loaded for 9 seconds and unloaded for 1 second. At full load there would be no solenoid valve switching at all, and below 10% load the compressor turns off. No oil return cycle is required, and there is no need for an oil separator because no oil is pumped out when unloaded and full pumping of the oil occurs when loaded. Unlike inverter compressors, digital scroll compressors produce negligible electromagnetic interference and certainly well below the regulatory levels, especially in the area of the 5th and 7th harmonics. Now we know how the concept works, let's have another look at the Copeland animation of the inside of the compressor. Removing the shell, we see the driving motor. With the motor removed, we see the drive shaft. And then, on closer inspection, we can see the orbiting effect produced by the eccentric shaft. Now we can see the scrolls in the engaged and loaded condition, and compression is taking place. Then, as the solenoid valve energizes, we see the top non-fixed scroll lifting just a millimeter, and all compression ceases. The cycle repeats and repeats continuously as dictated by the control signal. So, to recap, seamless capacity control from 100% down to 10%, operating cost savings of about 30%, better humidity control, negligible electromagnetic interference. Copeland digital scroll compressors are available in air conditioning and heat pump units manufactured in Australia and New Zealand by Temperzone Limited.